this new stuff that we do today, most of which will be on exam 3, okay? So we're talking about polynomials. Okay, so we kind of defined it, but here's right now we're switching. So a polynomial function with input x, it's the sum of monomials. So it's something, sum of terms, difference of terms, with whole number exponents and real coefficients. Whole number exponents, real coefficients. That means you can have only 0, 1, 2, 3, 4, 5, 6 as your exponents, and then, but then the coefficients can be any real number, pi, decimals, negatives, big numbers, small numbers, any real number. Okay, there's two forms of polynomial. Standard form is where it's truly written out as the sum of terms, sum and difference of terms. So that's your standard form. Factored form is where it's actually the product of factors. So if you were to multiply out this whole expression here, it would look something like this. It would end up being a bunch of terms. And so some polynomials they do have a factored form, others do not. Okay? But so here's one that has a factored form. Okay, so just some basics here. The Y-intercept. What would be true about the Y-intercept of a polynomial? So here's just a sketch. So what would be true about the Y-intercept? You're all thinking about it, right? So you're saying when x is equal to 0. Agree with that? No, isn't the Y-intercept when y is equal to 0? Yeah. What's equal to what is true about this point right here? Is y equal to 0 or x? X is equal to 0. And so, for instance, if it were this function here, how could we express the y-coordinate of the y-intercept? How could we express it? Cameron, what do you think? So I don't want to do the math. I just want to express what that y-intercept is. How could I do that easily?
I don't know.
Not sure. Yeah, Jacob.
It's one that doesn't have a coefficient in your standard form, so it's a lot lower.
No, this is from this function.
Oh.
So how could I, if I had drawn this one right here, how could I easily express the y-coordinate? Carlo.
Replace x with 0.
Replace x. Well, I've already done that. I want to express the y-coordinate. I know Jacqueline knows. Michael. Hopefully many of you were thinking that, okay? Yes, g of 0, right? The y-coordinate on a graph, we use function notation, because function notation gives what about a function? It expresses, what about a function does function notation express? Okay, y-coordinate on a graph, but just generically, what does it express about a function? Function notation. Output, right? And output is our y-coordinate, or vertical coordinate. For conventionally, that's how we graph things. Okay? So, function notation gives output of a function, and therefore expresses y-coordinates on a graph. If this is x equals 3, what are the coordinates at that point? What are the coordinates at that point? Jay, what do you think? So if this is at x equals 3, then how can I express the coordinates of that point right there? Well, there's an x-coordinate and a y-coordinate. How could we express the x-coordinate? Jay? 3, right? How could we express the y-coordinate of that point? I know Jenna knows. Kelly, what do you think? I know Jacob knows. I know everyone who's raising their hand now. I know they know. Maddie, how could we express the y-coordinate of this point?
Is it G of 3?
G of 3. Function notation, this G of something, right, is an output. And outputs are, that's the corresponding output when the input is 3. If you couldn't answer that question, from now on till eternity, be able to answer that question. Okay? Function notation expresses output, and output is our y-coordinate for that input. Super important. Okay. All right. So we talked about the y-intercept. That's where x is 0. So therefore, the y-intercept could be expressed as g, like in this case, g of 0, if this is the function g. Okay. So then, what we call the roots. Red for roots, or zeros. What's 0 with those? So if we're talking about a 0 of a function, then we're talking about the output being 0. Okay, this is all values of x that make the function 0. Or make the output equal to 0. Okay? So how many am I showing in my sketch? How many zeros or roots are shown in this sketch here? 2, right? So you've got some x-coordinate here whose output or y value is 0, and then another one here. So if we were to write this ordered pair, what do we know? I want to write the ordered pair of this point. What can I write down quickly? Freddie.
The x value and the y is 0.
The y is 0? What about the x value? Is it 0?
No.
Something, right? Something negative. Okay? But the point of a root or a 0 is the output of the function is 0. It gives you 0 when you put that input in. And so that's going to have a y-coordinate of 0. Okay, so that's just some basics. Take a look at this. So are these polynomials the same or different polynomials? They the same or different? Clearly different, right? So obviously they're giving different output values for the same input. Okay, well, what's this? Dang it. Wow, just out of control. There we go. Are these polynomials the same or different? Are these polynomials the same or different? Different. What if I had shown you like this first? What would you have said? You said the same. You said the two graphs are the same. What's going on here? So can you read? I know that the numbers are small. I cannot adjust the numbers on the axes. But this is 2 times 10 to the 7th. What is that? Is that 20 million to the 7th? Is that right? So this is 20 million. And this is 400, say here. So what's going on here? Yeah.
Well, basically, they're different polynomials
Okay.
with different numbers, but if you're looking at just the graph from a certain perspective, they look actually the same.
Right. Okay. So we want to be more. So I gave you a different perspective, and you would have answered differently had we started with this perspective. Yeah. Aaron.
Increase the Y max.
What's that?
You increase the Y max.
Okay, I increased the Y max.
By 11.
So what? So what's going on here?
You see it more far away. Going
Okay, will that be true about any two polynomials? If as long as you zoom out far enough, will any two polynomials be the same? Same degree. She said the same degree. Okay, so we're looking at, what kind of x values am I looking at here? When I started, we were looking at x values like 0, 1, 2, 3. Now what kind of x values am I looking at? Large, right? So large positive x, and then large negative x. Okay, this is the idea of what's called end behavior, meaning the far right end and the far left end. Okay, the far right end is really big positive x values, and the far left end is really, really big negative values. These two polynomials have the same end behavior. Okay, and let's see why. Why do they have the same end behavior? So when you look at very, very large x values, negative and positive, they virtually look the same. And if I got into the x equals thousands and hundred thousands and millions, well, it would be indistinguishable. The values would be pretty much indistinguishable. Okay, the output values. So let me show you these two polynomials. Okay, I got x squared plus ax squared, or x cubed plus ax squared minus 20x, and x cubed. So these two have the same end behavior. They have the same end behavior, meaning for very large values of x, for very, very large values of x, they're going to be virtually indistinguishable. Okay? They're virtually indistinguishable. But for values of x like 0, 1, 2, 3, 4, which is like middle behavior, those are not large values, clearly totally different, right? Totally different. So why is it that their end behavior is the same? So let's talk about x equals 1,000,000 here. If x equals 1,000,000, say 1 times 10 to the 6th, how would x cubed compare with 8x squared? If x was 1,000,000, how would x cubed compare with x squared? What's that?
X cubed would be a lot bigger.
It'd be a lot bigger?
Yeah, x squared wouldn't be very significant compared to x cubed.
Well, why not? Why not?
Because x cubed is 1,000,000 times more.
Oh, she's saying x cubed is 1,000,000 times more than x squared. Is that right? Is that what you're going to say? That's the point. When you get to x equals 1,000,000, now that term now is 1,000,000 times bigger than the x squared term, which is 1,000,000 times bigger than the 20 to the x. So for large x, for very large x, are these big or small compared to this? Small. So, and now a trillion. So if x was a trillion, now that thing's a trillion times bigger than that. So what happens is for very large x, anything that's not of the highest exponent basically is like 0 compared to the term with the highest exponent, and that's what Becca said, the degree. So all we look at, if we want to know what's happening for very, very large x, we just look at the term that has the biggest exponent. That's when x gets big, that one's going to dwarf all the rest of them. It's going to be so much bigger than the others, it's virtually like the others are 0. Have no effect. And that's what happened when I zoomed out into the hundreds, right? All I needed to do was get to the hundreds and they almost were the same. But imagine the thousands, the millions, the billions. Okay? This virtually disappears. These virtually disappears. So if you have a complicated polynomial and you want to just talk about the end behavior of it, what do you look at? You look at what's called the leading term. The leading term is the one with the highest power. Okay? So, and this is the kind of thing we do. So if we didn't have the graph, we would look at this first one and we would say, all right, let x be a really big positive value. So let's just turn off the graph here. Let x be a really, really big positive value. And the way we say that is we say x gets really, really big. Then, what would x cubed do? So, I'm sorry. So we want to distinguish between positive and negative. That's what we're doing. So if x becomes a really, really big positive number, then what about x cubed? Will it be really, really big positive or really, really big negative?
Positive.
Really big positive, right? And then if x becomes a very, very big negative number, then what about x cubed?
Negative.
Okay, because it has an odd exponent. When you multiply a negative together 3 times, it's going to be negative. All right, so for the end behavior, so we're saying as x gets very, very large positive, this graph is going to do what? Go up or go down? Nathan, what do you think? So for really, really large x values, is this graph going to go up or go down?
Up.
Because?
Because I guess positive.
Yeah, so because x cubed will be a big positive value. And as x goes, it gets very, very large negative, what will x cubed and therefore this graph do? Go up or go down?
Down.
Down. Right? Down because x cubed, if x is a large negative number, will be a very, very large negative number as well. And that's what we saw. When I zoomed way out, the behavior of it just became like x cubed, which is like this. Okay? This is the idea of end behavior of a polynomial. So a couple practice problems are, I think they're in your book. Let's see here. It's the wrong module. That's the right one. Where is it? Gee whiz. All right, here we go. Here we go. So number 7. What page? Someone find this. In, module 5, investigation 5, number 7. Is it still that? Sometimes the PowerPoints are different from the book. As soon as you find that, tell me where it is. What page? Here. Page 199, it's number 7 is still the same thing. So all I want you to do is figure out what's the end behavior. What's the end behavior of this without graphing it? So it's not by looking at the graph, but by reasoning this out. So if x is if you go way out to the right, meaning x then what does y do? And you're reasoning based on the formula. You're not graphing it and looking at the graph. You're reasoning based on a very, very large positive values of x. What will the y values do? And then, for very, very large negative values of x, what will the y values do? Okay? So, take a couple minutes, or a minute or two, and see if you can do it. Not by looking at the graph, but by reasoning through the formula. Okay? This isn't about memorization or, it's about understanding what we talked about and making these conclusions. Okay? So you take a minute, work together. How about Cecilia? So if x is really, really big positive values, then what would we predict y would be and why? So can you talk me through it?
Yeah, so I don't know if this is right, but I thought it could be both in a way. Because if you put in a positive number for the first one, the 9x squared,
Okay.
if you subtract 4x,
Mm-hmm.
4 times whatever number you put in could be, like the result of that could be greater than
Okay.
the previous one, so that could be negative
All right.
1. And then if you put a positive number into the 2x to the 4th,
Mm-hmm.
that's going to be positive, negative.
Okay, so you're kind of missing a key point that we made here. When you're looking at really, really, really big numbers for x, what are we going to focus on? Do we consider everything?
Would it just be the 2x to
Yes. Why?
the greatest exponent?
Okay.
That's like the biggest.
Right. Imagine if that x was a billion, then how would this term compare with this one?
Would be greater.
It would be greater, yes, by a billion squared, right? Because this is to the 4th, and this has two more billions multiplied by it than this one does. So yeah, it would be greater. What about this one? This would be a speck in the universe, right? Right? This would be a billion times a billion times a billion times greater than that. So when we focus on, figure out what's happening for big x values, we only look at, well, it's more than just the exponent. It's the term, the leading term. We can look at the leading term, okay? So now x is a really, really big, okay, answer.
Well,
Yeah, go ahead.
answer to the if x plus 30 then y.
Yeah, so for really, really big positive values.
So in this case, it would initially be positive, but it would slope downwards, further and further and further and further and further and further. So if you were to draw that, it would be like.
Don't tell me about the picture. Reason numerically. So reason about the numbers. What's happening with the numbers? Why are you concluding that?
Because x, I don't know, 4th.
X to the 4th.
Because x to the 4th will inevitably completely overwhelm the other exponents.
Okay.
It will be far, far more important in the long run.
Okay. We've established that. But now we're trying to get a conclusion for what y will be.
Because it will be so overwhelmingly huge, it will force, because it's a negative, it will force the graph downward.
Okay. So he's saying because of this negative here, y has to be negative.
Well, no, it doesn't. That's not what I said.
That's what I heard.
Initially, it will be positive.
What's initially? So tell me.
At x equals 1, it will be positive. But it will go further and further. It will slope downwards and slope faster and faster downwards.
Okay. Aaron, go ahead.
So like even if whatever x is was a negative, if you multiply it 4 times, it would be a positive. But then you have to multiply that number by
Okay.
-2.
We're talking about we're just talking about this first one here. X is a really big positive value. X is a really big positive value. Nick,
It's really, then y is a really big negative value.
because why?
Because if you do it x to the power of 4, so
Yeah.
really a billion to the power of 4 times -2.
Okay.
It's an even exponent, so it's not going to change the sign.
Okay. Right. There's two things involved here. X to the fourth, first of all, will give us a really big positive or a really big negative. X to the fourth. There's two parts to this. You have to break it down. There's two things going on. X to the fourth by itself will give you a really big positive. But then we're taking that really big positive and doing what? Multiplying it by -2. Therefore, the result, really big negative. So like Dan said, the graph will go down to really big y values that are large negative values. Okay, how about x negative? Somebody new. How about Sean over there? What do you think? So talk me through this. If x is a really, really big negative number, then what's y going to be?
It will also be very negative, approaching negative infinity.
Can you talk me through why?
Well, it's to the fourth, so again, it doesn't change the sign there as well, or,
Well, it doesn't change the sign, so it's negative. X to the fourth is negative.
well, x to the fourth negative would actually be positive,
Okay.
but then since you're multiplying that by the -2, that makes it negative.
Okay, so a really big negative number to the fourth power is a really big positive, and then we're taking that positive and multiplying by -2. Final conclusion. So if we were to draw the end behavior of this, going out to the right, we would go up or down? Down. Going way out to the left? Down again. So when you look at that leading term, there's two things happening. You have to look at just the exponent, applying the exponent, and then you might have to then apply a negative on top of that. Is there another one? All right, let's do this one. Do f of x, and we'll be done. So just the f of x function. So as x gets really large positive, or we go way out to the right, will we go up or down? And as x goes way out to the left, then will we go up, or will the graph head up or down? So for this one, f of x. John, help me with this one. So let's do, how about really big positive values? What are you going to look at here in this?
3x to the 6th.
3x to the 6th. So way out to the right,
It's going to be positive.
because?
X to the 6th gives you a positive
Uh-huh.
times 3 is equal to 1.
So up or down?
Up.
Up to the right. Way up to the right. Okay, to the left. Let's see. Jonathan.
It's going to be
So we do big negative numbers. What will happen to big negative numbers in this? Positive. Because of the x to the 6th. And then we multiply it by positive 3. So way out to the left, you're going to go up or down? Up way out to the right and up way out to the left. Okay, any questions on end behavior of polynomials? Okay, so let's move on to rational functions. Okay, a rational function is a function expressed as the ratio or fraction of polynomials. So if you take one polynomial and divide it by another, you've created a rational function. So I've called n of x. This is our polynomial that's in the numerator, and d of x is our polynomial in the denominator. So when you do this, when you take one polynomial and divide it by another, you get all like these nice smooth pilly functions get crazy. Okay, so if you try to divide one by another, you get all these crazy situations that can arise. Those rational graphs, they're crazy. So we'll just examine a little bit of this. So in your book, if you go into Module 6, first thing we're going to look at is example number, investigation 1, example 2. What page is that on? It's about 5 gallons of liquid flavoring. What is it? 222. Okay? So I want you to start working on those. Number 2 on page 222. So let's just read it together. 5 gallons of liquid flavoring is poured into a large vat. Water is going to be added and mixed with the flavoring to produce a drink that will be bottled and sold. Okay, so you've actually got 3 different quantities that they're involved in the questions here. So you really have to be actually there's 4. There's like 4 quantities flying around here in their questions. So to be very sure and confident about what they're asking about. Okay, so just that's your warning. 4 quantities in play. Okay. So read carefully and know in any given question what are the focal quantities that they're drawing you to. Okay. Okay, so A and B are to help you get the idea of what's going on. And then in C, you got to be really careful that you are understanding what quantities they're talking about in C. So draw upon your answers in A and B. So I'm going to come around and see your work on this. That's in the book. That's the textbook. You won't find it in there. Because the workbook is different. That's not in the text. Okay. Can you share with me? Get it out. Use the chair. By ratio, they want you to find a value, a value. Does that make sense? Yeah, so just let's do A, B, and C. A, B, and C. Ratio of flavors. Okay, so you'll need to. So by ratio, they're talking about a value, okay? Not 2 values, they're talking about a value. By ratio, they mean a particular value. Okay, this one over here. Did you get the part A? The ratio of flavoring to water. What would that be? 5 over 2. He wants 5 over 2. And where'd the 2 come from? Can we rewrite that as?
7 minus.
That's going to help us down the road. Okay, so he wants the ratio of flavoring to water to be 5 halves, which came from 5 over 7 minus 5. Did you hear that? Cool. All right. How about the total, the ratio of flavoring to water when the total mixture is 18? Fahia. 5 over 13. And where did the 13 come from?
18 minus
Are we good on A and B? Okay, so that's, we've got to really understand A and B to have a fighting chance at writing the function correctly. So is the output of the function in C, is it the ratio of flavoring to water? Is that right? Okay. So now, and the input is what? So I'm going to define this function. How do I start defining this function? Zach?
F of x is like input.
Good. Okay. F of x. Function definition. Here it comes. Or the whole thing is the definition. Here comes the rule. So how do we, given an x total volume of mixture, how do we get the ratio of flavoring to water?
X over x minus 5.
X over x minus 5.
Or 5x minus 5. 5 minus x.
Okay, so is this the ratio of flavoring to water? You want to flip it now? 5 minus x over x? Let's do one thing at a time. So how much flavoring is in the vat? Amount of flavoring to amount of water. How much flavoring is in there? Always 5, right? How much water is in there if x total gallons are in there? X minus 5. Okay, can we calculate this ratio for a total amount of mixture of 5? Why not?
Because the denominator can be 0.
Okay, and what would it mean in the situation? Trying to make the total, right, the total amount of mixture?
It would all be flavoring and there'd be no water.
Okay. All right, so, right, it'd be all flavoring and no water. So we can't, but what we can do is we can look at what the next question says is, what does this mean? What this means is, let x get really, really close to 5. Okay? As close as you want, and then closer than that. And if that's not close enough, you can get closer than that. But don't ever really say x equals 5. Just get exceedingly close, or really, really close. And so it might look like a sequence of numbers like this. So we might be at 4, and we get closer to 5. It might be 4.5. And we get closer to 5, 4.9. And then 4.99. So this sequence of numbers is the spirit of x approaching 5. And then 4.9999. Get as close as you want. And then if you're not satisfied, get even closer. You can always get closer to 5. But we know that 5 will not be a valid input for this because we can't divide by 0. Unless you're Chuck Norris. Chuck Norris can divide by 0, but you guys can't. Okay? Alright, so we want to find the value of the function for these different inputs. These are valid inputs. Getting close to 5, as long as it's not 5, we can get an output. So I want you to find is a table like this coming up in the question? Anyway, it should be. Yeah. What's that? Oh, right. So we gotta have more. Yes, thank you. We gotta have more than 5. So hopefully you were all thinking that. So what do we gotta do? We gotta approach 5. So here's what we do. We add a little plus there. And that means approach 5 from the right, not from the left like your teacher. From the right means we're going to get close to 5, but starting with larger values than 5 and coming down to 5. That will make sense in this situation, right? Only numbers greater than 5 make sense in this because the total mixture has to be greater than the 5 gallons of flavoring. Okay? So we can start with like 6, and then go 5.5, and then 5.1, and then 5.01. Is this similar to, is there a table there for you already like this?
Yeah.
Okay. So these x values are the spirit of x approaching 5 from the right. From values larger than 5 and getting closer to 5 from the right side of 5, if you think about the number line. So we want to find these, since these are all valid amounts of total mixture we could have, find the corresponding output or this ratio of flavoring to water. Go. So we're going to find these output values, if you haven't already. Bummer. I thought they already gave it. Okay, what's the ratio when x equals 6? Go ahead. Nice and loud. The ratio is 5? Okay, what about 5.5? Anybody get it? Just shout it out. 10. So there's 10 times as much flavoring as water when the total amount is 5.5. What about 5.1? 50. 5.01.
500.
I see a pattern.
5,000. 50,000.
Okay. Tell the person next to you, what does that number mean? What is that 50,000? What's that about? What does a 50,000 mean according to the drink and the vat and the water and the flavoring? Go. What does the 50,000 mean? Okay, Andrew, what do you think? And why is that true?
Units of flavor for every 1 unit of water.
And why is that happening? So what caused that? It's because we were adding a lot more flavor, kept adding more and more flavor. Is that what happened?
Because we added a little
How much water did we add? Right, right. Okay, so when the total amount of gallons in that thing is 5.001, what does that mean for the amount of water? Valerie, so what does that mean for the amount of water when the total mixture is 5.0001?
Then that means that there's 5.00. That means there's 50,000 more flavoring than water.
Okay, and why is that true? Why is there so much more flavoring than water? Because we dumped all that flavoring in, so we just kept adding more and more flavoring?
I thought you were adding
We're
water.
adding water. Okay. So why is it 50,000? What's happening? What's causing it to be 50,000? Janessa?
Well, I was thinking 50,000 was like the total number of gallons in the vat when X is the number of gallons.
Okay, so there's 50,000 gallons in the vat. So it's like we're adding tens of thousands of gallons of flavoring.
No, when X is the number of gallons of
Okay, so X is the number of gallons. Okay, it's,
then R of X is the number of gallons in the vat.
okay. That doesn't really make sense. Let's see, Michael.
So the X is your.
Okay, so look, this underscores the point. You have to be really confident. If we're going to talk about, we have to be really confident what these two quantities are. All about quantities, right? So that's where we got a little bit off track. So what quantity is X? Total in the vat. Total gallons. And so without being confident about what our quantities are, and what is the output? Ratio of flavoring to water. So that 50,000 is not a number of gallons, but it's a ratio of flavoring to water when there's 5.001 total gallons in the vat. Okay, so Cameron, can you tell me what's going on here? What's that 50,000 about then?
Means that there's 50,000 times as much flavoring as water.
And why is that true?
Because we add less and less water each time.
How much water do we add this time?
0.001.
Yeah, it's like, right, so it's like what? We had this 5-gallon tub of flavoring, and what did we do? What did we do? We took a big thing of garbage pail of water and we poured it in, right? Right? No, what did we do? Okay.
Just a little 0.001, so it's like a little bit of water.
Yeah, like a drop, like a part of a drop of water, right? So it's like ding. And so now, what about the ratio of flavoring to water now? Of course, it's going to be much, 50,000 times as much flavoring as water because there's the 5 gallons and now this like part of a drop of water in there mixed together. Okay, so what will the graph look like then close to 5? So now you know that as you put less and less water in, our total mixture gets closer to 5, and then so the ratio of the mixture of the flavoring just skyrockets. So can you imagine what the graph will be like? Let's do it. Let's just graph it. What's our function? 5 divided by x minus 5? Okay, 5 minus x? Or x minus 5? X minus 5. Okay. So what's this going to look like? First of all, where does it make sense? For what values of x does it make sense? X. Yeah, the total mixture has to be greater than 5, so we're just going to look at where it makes sense for the total mixture to be greater than 5 gallons. And so draw it with your finger. So here's 5 over here. So can you just sketch in your mind what the graph is going to look like there, starting at x equals 5? Draw it with your finger. Everyone do it. What was that, Zach?
What, that?
You go like this?
That, yeah.
Not tracking. So let me zoom out here. So here's our ratio. So as we add less and less water, here's 5 now. As we add less and less water, what happens to that ratio of flavoring to water? Dan?
Skyrockets.
Skyrockets, right? So that's what we're seeing there. It skyrockets. This is the idea of a vertical asymptote. Because we can't plug 5 in there. It's undefined. This function is undefined at 5. But as you get close to 5, function just gets very, very large. The closer you get, the larger this the value gets. This is the idea of a vertical asymptote. Okay? And so vertical asymptotes then are what? They show up at the roots of the denominator function. So, and that's only so that and that's true if that same number is not a root of the numerator function, like we have here. The numerator function has no roots, right? It's just 5. There's no way to make that 0. So as long as you don't have the same root in the numerator and the denominator, and you only have that root in the denominator, you get a vertical asymptote. Okay, please.
Can I get a spelling of that? 'Cause it's really hard to read how you wrote it. Just notice.
Which one? Asymptotes?
Yes.
You bet. Asymptotes.
Thank you.
You're welcome. All right. So the roots of the function will be the roots of the numerator. So where this function has zeros, the output is 0, will be the roots of the numerator. And then the roots of the denominator will be the vertical asymptotes. This is your crash course on the roots of the numerator are the zeros of the function. And the roots of the denominator are these values where the graph can never cross, and as you get close to them, they get very large positive or very large negative, negative values like the flavoring example showed us, okay? Now, that is to say if as long as that root is only in one place or the other. When you have the same root in the numerator and the denominator, it's something different, which we won't cover, okay? So you can only have that root in the denominator, gives you a vertical asymptote, or only have a root in the numerator, that gives you a root of the 0 of the function. Okay, so let's look at end behaviors of these things. So the end behavior of a rational function so if we have our n, where is it? I'll just read it right again. So if we have our nx over dx, so what are we going to do? We're going to look at the leading term of the numerator. Why? Because that's what we look at. So when x gets really, really large, positive or negative, then that leading term is going to govern. And then we're going to look at the leading term of the denominator. And so that we'll get a ratio, when we do that, we'll get a ratio of monomials. And that ratio of monomials is like the effective leading term of the whole function, okay? So this function doesn't have a leading term because it's the ratio of two polynomials. But if you take the ratio of the leading terms, then whatever that turns out to be, in effect, is like the leading term of the whole fraction. So we'll call that effective, because there's not really a leading term, but in effect it is. So it's the effective leading term. And that effective leading term comes from the ratio of the big leading term of the numerator and the leading term of the denominator. And so we analyze that ratio, or whatever that ratio turns out to be, and just like we did before, and then so whatever that does is what this function is going to do for large positive and negative values of x. Okay? So let's do some examples of that. I had some here. So in your workbook, and there's where is it? Module 6, investigation, PowerPoint. Oh, come on. Just give me a... Here we go. Investigation 3, number... Do those 4 show up? Investigation 3, did you see those 4 in your book? Okay, what we're going to do is you're going to find the effective leading term for each one. So we're going to determine that just the end behavior. Okay, so we're just interested in end behavior here. Okay, so I think, is that 4? Okay, so what we're going to do is they talk about horizontal asymptote, we're not going to talk about that. We're going to talk about, we frame this in terms of the effective leading term. So look at 1. How would you find the effective leading term for this first polynomial here? So you look at the leading term of the numerator and the leading term of the denominator, and you take the ratio of those. So for number 1, the effective leading term is, so for f of x, effective leading term is what? X over x, and then we can simplify it to 1. So this is the leading term, meaning as x gets really, really big positive, what does the function do? Yep. It gets closer and closer to 1, right? So it's virtually like 1 when x gets really, really big positive. What about when x gets really, really big negative? It's going to virtually be 1. So the effective leading term is this is the graph y equals 1. So if the end behavior of this is just like the graph of y equals 1. Okay, so for number 1 here, as x gets really big positive, the output of the function is going to get close to 1, whatever the leading term is. And the leading term here is just 1. When it decreases to negative infinity, it's going to be like that. Whatever that does at negative infinity, which is 1. Does it make sense? Okay, what's the effective leading term in number 2? We have to multiply out the denominator. What's the effective leading term in number 2?
3x.
I heard 3x. I heard 3x squared. It's going to be 3x squared over x squared. And we can simplify that to 3. So the effective leading term is 3. And so way out at the ends, this is going to behave like whatever y equals 3 behaves like. So as x gets really, really large positive, it'll get close to 3. The horizontal line, right? The horizontal line 3. As x gets really large negative, the graph is going to behave like this, like 3. Okay, number 3, effective leading term. So for h of x, what's the effective leading term? X squared over, which is x. So now, when x gets really large positive and negative, the function's going to behave like x does, like the function y equals x does. The effective leading term is x to the first. So, and we'll show all these in the graph. But anyways, when x gets really, really big positive, will it go up or down? So if x is a really, really big positive number in the function h, for large positive values, it's going to be like y, like x. So, way out to the left, way out to the right, is it going to go up or down? Up, and better than that, it's going to go up and it's going to be just like the line, y equals x. And when x gets really, really large negative, it's going to go down, and it's going to be like, again, like y equals x. Because when x is really big negative, it's just going to be whatever that number is. Okay, last one, k. So for k, what's the effective leading term? 5x over x squared, which simplifies to 5 over x. So for large values of x positive, the graph is going to be like 5 over x. The graph is going to be like 5 over x. Okay? So what is that? For large positive x values, the function k will do what? Be like what? What will that do for large x values? 5 over x. So 5 over a million, 5 over a billion, 5 over a trillion, 5 over a Google. You know what a Google is? It's not a website. It's not a search engine. 100 zeros, 10 to the 100th. That's a Google, long before the internet even existed. Okay? 10 to the 100. That's a Google. So 5 over a Google. What is this? What is that going to be like? Approaching 0. This is going to be virtually 0, right? And then also when you put in really big, large negative numbers, 5 over a huge negative number, it's going to virtually be 0, just coming from below instead of coming from above. Okay, so let's see this in action. So what was the first, let's see, this one's interesting. So let's do h of x. Let's do h. X squared plus 1 divided by x minus 2. Okay, so in the middle, we've got crazy things going on. We've got the asymptote at x equals 2. There's no roots. There's no values of x that make the numerator 0, so it never crosses the x-axis. But what's going to happen if I zoom out? What was our effective leading term? X, right? So watch. I'm just going to zoom out on the graph. And what do you see? What is that? Y equals x. That's the graph y equals x. And that was our effective leading term, x squared over x. So here we're at, what are we in? Tens of thousands and tens of thousands. Virtually this rational function is like x. Let's do, that's pretty cool. How about let's do this one, g of x. 3x squared over x minus 1, x minus 3. Uh-oh, I don't know what that. Reset. Okay, so here's this crazy graph. Oh, you're not saying that. Really? It's different?
Yeah, well, it's not 3 and multiplied by the entire thing, it's 3x squared over.
It's different? Is that the same?
It's different.
3 times a over b is different than 3 over b? Is that what you're saying? They're equal. They're equal. 3 times a fraction is like 3 times the numerator.
That's right.
Yeah. Okay. All right. Okay, so it's all crazy in the middle here, right? And what do we got? We got roots. What are our roots? We have a root at 0. There it is. And we got an asymptote at 1, asymptote at 3. Okay, so that's our x equals 1 equals x equals 3. And what did we find for the effective leading term? We did 3x squared over x squared, and we got effective leading term of 3, which means that for really big values of x, not too much. For really big values of x, here I'm in 50s, hundreds. Here's the hundreds. Here's the thousands. Here's the 10,000s. I'm still graphing this graph right here. It's still this rational function, but I'm in the up to the millions now. And what is it just like? For large values of x, that rational function is just like y equals 3. Okay, so you got your exam right now, and we'll have an assignment, so hopefully it'll be shorter. I'll see you Tuesday. We'll start trig on Tuesday. Yeah, just go to the window 216. Okay. And say that there's an envelope for me in the file box.
Okay.
And it has the Scantrons and the tests.
Okay, sounds good.
Thank you.
Yeah, you're doing the investigation.
That's literally the
One place, well, how are we going to start that?
Band-Aids? No, I don't have Band-Aid on me. I'm sorry. Are you okay?
Yeah, it's good. I haven't yet started.
Oh, you scratched a little too much, huh?
Yeah.